This lecture will be going over errors and inferences, how we can use the sources of errors in our experimental process to aid our ability in making inferences about our high-level scientific hypotheses. The reading for this lecture is Mayo, Error Statistics and Learning from Error, Making a Virtue of Necessity from the Philosophy of Science. If you have not read this, please pause, go read it, and come back. Today's lecture has 3 topics. First, we'll go over the difference between evidentiary approaches and existential approaches to scientific inference. Then we'll go over a framework of inquiry proposed by Deborah Mayo as how to apply error statistical approaches to scientific inference. And we'll end with a case study or an example of this approach in practice. So starting at the beginning, what are evidentiary versus existential approaches to scientific inference? And these map along dimensions that we've talked about in prior lectures. So let's start back to the beginning. This might look familiar to you if you saw our initial lecture on quantitative epistemology. The hypothetico-deductive model of science was a model of science proposed by Heppel and Popper in the middle of the last century, and it outlines kind of how you move back and forth between deductive reasoning and inductive reasoning in this cycle of theory evaluation. So you start with some high-level theory that allows for you to deduce consequences and make predictions, which form hypotheses. From those hypotheses, you design experimental tests for specific observations. Then you determine the outcome of those tests, and you determine the generalizability of the effect, whether or not your predictions were right or wrong, and how wrong were they. And you use this information to reframe your concepts in your theory and redevelop your propositions. And this loop is a continual refinement of a scientific theory. On the right-hand side, the initial side, you have deductive logic. And on the left-hand side, you have inductive logic. You're using observations to induce a new form of your theory or refine it in some way. And for the moment, I'd like to pause and focus on this inductive logic here, because this becomes something of importance when it comes to scientific inference. And in fact, if we go back to our discussions on the problem of demarcation, which was proposed by Karl Popper, you start to see the limits of this inductive side of the inference cycle. Now, what is the problem of demarcation? Well, remember, this is what Popper was trying to argue distinguishes a scientific theory from a metaphysical theory, or in other words, an empirical theory from a non-empirical theory. And Popper contrasts 2 points: the modus ponens approach, or inductive reasoning. The typical form looks like this, which translates into English that if P then Q, thus if P is true, Q is also true. So for example, there are black swans. This statement requires an exhaustive search to be validated. You have to keep searching until you identify a black swan. Now, inductive reasoning was the popular form of scientific inference in the early half of the 20th century. Once Popper's landmark book was released and follow-up work by others pushed the idea that we need to infer from modus tollens, deductive reasoning, which has this form, which can be reframed as if P then Q, thus if Q is false, P is also false. So the classic example is all swans are white. All you need is one counterpoint to disprove this hypothesis. And according to Popperian logic, you can only evaluate a scientific hypothesis using modus tollens, using deductive reasoning. And if you want more understanding as to why this occurs, please go back to that lecture where we were talking about forming scientific hypotheses. But for right now, you can see how these 2 approaches to inference present 2 possible philosophies for evaluating hypotheses. On the one hand, you have evidentiary hypotheses, which use inductive logic and Bayesian reasoning. So this is a very common way of approaching scientific inference from the Bayesian perspective, which essentially answers the question, how well does evidence confirm or support a hypothesis? And according to Deborah Mayo, we'll call this the evidential relation or ER framework. So this uses strictly inductive logic in order to build up evidence to support a hypothesis. And this can be contrasted with existential approaches, which use deductive logic and are very popular amongst frequentist statistics. And the existential approaches answer the question, how does the evidence discriminate between hypotheses? And this relies on the error statistical approach that Deborah Mayo proposes in her article. Now, you can see how these two approaches have fundamental different aims. Evidentiary is asking how well does the evidence support a hypothesis, whereas existential is asking, does the hypothesis exist? So let's dig into this a little bit more and focus first on this inductive approach, because it's the non-standard approach if you've taken a basic statistics or statistics for science class. And we've actually gone over this in a prior lecture. If you can recall, going back to the lecture on Bayes factors, a Bayes factor is a Bayesian approach to determining the evidence towards one hypothesis over another. So the Bayes factor is just determining what the ratio of evidence is between two hypotheses. And so here we have that form that we've gone over before. You have the probability of hypothesis 0, or the null hypothesis, given the evidence y, over the probability of hypothesis 1, your target or goal hypothesis, given the evidence. And this can be framed as a ratio of evidence between the likelihood of the data given the two hypotheses times the prior probability of those two hypotheses themselves. And what you get with this inductive Bayesian approach is you can determine the relative evidence for one hypothesis against the other. And so a Bayes factor, generally IJ, identifies whether the observed data are more likely to arise from hypothesis I than from hypothesis J. And you can use this to compare multiple forms of hypothesis, but what you get is this continual measure of evidence. And as we showed in the prior lecture, this is very useful in some certain cases. Now, this ratio of evidence idea can be contrasted with the concept of a null hypothesis and null hypothesis test statistics, which we talked about in our prior lecture on the atom approach to using p-values. So in this case, what we're doing is not evaluating the evidence for one hypothesis against another. Essentially what we're asking is, what is the probability that one hypothesis exists? In this case, we're often using the null hypothesis, which can be framed as the probability that you observe your data if your predictive relationships are not true in a special case. So you might have this distribution of the null hypothesis, the probability that the null hypothesis is true. And on that curve, you might collect a particular experimental test that sits somewhere on this curve. So the classic example is a t-statistic. If this is a distribution of t-statistic values given a null hypothesis of 0 difference between the means, you have some evidence, you calculate your t-statistic, that gives you your observed effect, this line over here on the right. And then everything to the right of that is your probability of the data given that the null is true. And that'll give you your p-value. Now the p-value is used to make a very strict decision. Does the null hypothesis exist or not? So it is fundamentally an existential approach. Now you can think about this as just being two general philosophies with differences in aims. The evidentiary approach wants to know how you can update the degree of belief in a hypothesis based on the evidence and prior probabilities. Whereas the existential approach uses errors as a means of evaluating the existence of a given hypothesis. At a fundamental level, what you're saying is, have I come to this data that has this particular outcome, given that I'm wrong? What is the probability that I'm wrong? Which is another way of saying, what's the probability that my null hypothesis is true? So you're strictly trying to determine the existential probability. Now, Deborah Mayo makes a strong case for adopting the deductive existential approach, and she highlights two important virtues of the method. One is that This allows for including evaluations of your model before evidence is even collected. With the evidentiary approach, you're really just taking your data as it is and evaluating multiple forms of a hypothesis and comparing those against each other. But you need to have the data up front. Using the existential approach, you can include prior understandings of different sources of errors or how errors could occur in the design of your statistical tests itself. So you can include these evaluations before you've even collected any single piece of data. Also, these approaches don't equate scientific inference with a direct application of a statistical test. Now, this is where these methods are often misused, but in a pure sense, the existential methods don't necessarily directly assume that because a statistical outcome occurred that you were correct. In fact, by default, they assume that you're incorrect, and you have to keep showing how you might not be incorrect. So at a pure level, at a pure philosophical level, the existential approach, the deductive approach, won't just take the outcome of a statistical test and use that as a strong confirmation of a hypothesis. No. Your hypothesis has to be proven against tests that are trying to show that it is wrong. And it is in this exhaustive testing that you can do scientific inference. So let's take a look at this error statistical approach proposed by Deborah Mayo. The fundamental goal of this approach is to determine the error probability of individual hypotheses. So this approach is fundamentally trying to look at sources of errors in the process of evaluating your hypothesis at multiple levels. Its origins trace back to the Neiman-Pearson model of statistics, which arose in the middle part of the 20th century and is kind of the basis for the modern frequentist approach. It fundamentally rejects the use of prior probabilities in determining the likelihood of a statistical hypothesis or scientific hypothesis. It evaluates models and how well they discriminate between alternative hypotheses. So the idea is that you're comparing your hypothesis against other hypotheses and asking which one exists, which one is true, given that it hasn't shown an error yet. It also thinks about a model as being only as good as how well it facilitates learning from error. And this ties back to the Popperian form of deduction relying on falsification. So a model is only as good as it allows itself to be rejected from error. The more it allows itself to be rejected from error, as in it makes bad predictions, the more falsifiable it is, and therefore more empirical it is. And finally, probably most importantly, you can only deduce incorrect models with this approach. That is, I think, something that's key that is often missed when we're talking about looking at the results of our statistical models and trying to evaluate hypotheses. The error statistical approach only says there's an error here, i.e. a model didn't make the prediction in accordance with what the data said, so therefore we can reject it. We think it is incorrect. But you can never really say whether or not a model is correct. You're always allowing for the possibility of there being an error in your framework that you just might be missing. And so in this kind of a way, you can only know what you can reject, but you can never know what you can accept. Now, to implement the error statistical framework, Dr. Mayo presents a framework of inquiry, how to kind of approach incorporating methods of experimental design, data generation, modeling, and testing into the process of an evaluation of a scientific hypothesis. But in order to understand this framework of inquiry, you need to understand that hypotheses and models sit at multiple levels. And this has been a theme throughout the lectures of this course. And Dr. Mayo makes a very specific case for 3 general levels of models in any scientific inquiry. The first is your primary models. These are the primary question of interest, the highest level theoretical hypotheses being evaluated. And in most cases, when we talk about evaluating hypotheses, we're talking about evaluating them at the primary level. But underneath that, and as we made the case for in the lecture on developing a scientific hypothesis, you also have models at the experimental level. And these are models of the statistical form that link the primary models to the data itself. This is that formalism of your primary hypothesis into the structure of a statistical model. But you also fundamentally have models of the data itself. You can think about this as assumptions about the underlying form of the data. So for example, the distribution assumptions of your data for, let's say, a linear regression model. In order to evaluate a scientific hypothesis, you need to think about the multiple levels that it can be evaluated on. And in particular, according to Deborah Mayo's approach, you need to be looking for sources of errors at each of these levels of inquiry. So you have fundamental models of how the world works at these three levels, and you want to be looking for where errors occur at each of these levels. Because these errors propagate across this hierarchy of representation of your scientific hypothesis. So for example, if you have an error at the level of the data, maybe your data doesn't fit the distributional assumptions of the statistic you're using, that can influence the outcomes of your statistical model, the framework of your theory at the statistics level, which can influence how, at the high level, you evaluate the reliability or the probability of your theoretical hypotheses that are being evaluated. So you need to systematically think about each one of these levels of experimental inquiry and where sources of errors occur all the time in order to determine how severe of a test you have of your primary hypothesis. The more rigid each one of these models is and robust against errors, the more rigid and severe the test of your primary hypothesis being evaluated. So how do we learn from these errors? How do we develop approaches for optimizing that stepwise evaluation from primary models all the way down to data models in order to build these severe tests of our hypotheses? Well, Dr. Mayo presents a set of recommendations for how to learn from these errors. And we're going to go through in the order that Dr. Mayo presents, although it does kind of go out of chronological order from how you think about designing an experiment, but that's okay. So first we start with after trial checking. This is essentially correcting myself. After the data are collected, develop methods for evaluating how well the data matches the assumptions of the data model you started with. So, for example, if you assume that your data is normally distributed, run a test to confirm that your data are in fact normally distributed. So this is a way of saying I have my data on hand. I'm going to start from the bottom up. I'm going to start immediately afterwards making sure that I'm meeting those primary assumptions of the data model. The same can be done at the experimental model and to some degree at the primary model itself too. You also want to develop approaches for before trial planning. And this is the case where kind of knowledge of past mistakes and errors can influence the experimental design in order to prevent those mistakes or errors in the future. This is part of the proactive planning process. So in cognitive psychology a lot, you'll see catch trials introduced into experimental designs. These are trials to confirm that your participant is paying attention and doing the tasks they're supposed to be doing. And these are ways of building in checks for potential errors. So if you're running an experiment and you don't include these catch trials, these attentional catch trials, you might get data from a participant who's on their phone doing other things or just bored, not paying attention to the actual task at hand. And these sorts of trials allow for you to check and catch potential errors that can contaminate your inference process. Moving on, you also want to develop an error repertoire. And this relies a lot on experience, but you can also share the experience of others by asking people where those errors occur. But this is a list of known errors that have occurred in the past that you want to either avoid beforehand, before trial checks, or afterwards, after trial checks, in the future. And we went over this in some way when we were talking about data cleansing. So data cleansing steps are a way of taking known errors, known types of anomalies, building checks for them, and being able to vet or audit them. But there's lots of ways that you could do this. So over time, you want to have this repertoire of known kind of mistakes and errors that can happen at any one of those levels, from the data level to the statistical model and experimental level to the theoretical level itself. You also want to be aware of the effects of mistakes. You can look for them, but there's also subtle clues for the potential of mistakes. So knowledge of the effects of mistakes or errors allows for discriminating the effects from artifacts, true effects from artifacts. So for example, we know that fatigue reduces reaction times. If you have a very long cognitive psychology experiment and you see drift in the reaction time so that over time they get slower and slower and slower, then you know that there's a potential mistake in your experimental design whereby fatigue could be influencing your primary measure of interest. And so you want to have not just an idea of a repertoire of the known errors themselves, but also signatures and clues for these errors that you can then go back and try to correct for either in a revised experimental design or maybe in your data analysis itself. Building off of this idea, you can simulate errors. So you can build simulations, and these don't have to be computer simulations. You can simulate different types of errors in, let's say, a device that you're using to record your responses. You can build different types of situations that you run people through. But you want to simulate the presence of mistakes and errors to determine the effects of them on your trial outcomes. So if you're not sure, you think that your task might be too distracting, well, simulate that effect. Or if you think that your task might be fatiguing, simulate that drift in your reaction times to see how it impacts your predicted group differences. Right? So you don't have to necessarily start with this base of known effects. If you think that an error might actually introduce effects into your data, well, simulate those and see what those would look like. Also, you want to amplify and listen to your error patterns. So you want to be able to push your systems to detect as small as errors as possible by magnifying their effects. So sometimes if you think that you're really going to be coming up against sources of errors, you want to try to find your kind of range by which they present themselves. An example of this, continuing with our cognitive psychology examples, you want to shorten the trial windows to force people towards random guessing. If you're doing a decision-making task, by forcing people to just respond as quickly as possible, at some point people are just going to start guessing. And you should see no structure in their decisions. They're just going to be making random choices. And you now know that you can amplify and what your bottom limit is for your trial window in order to kind of wash away your effect. And so you can then use that to kind of push back out and see what your kind of lower response window is for your task at hand. Sort of the opposite side of this is focusing on the robustness of your effects. So you can take all this information that you've learned and you can understand, or you can start to make assumptions of when a background error or problem does not influence your outcomes. So you can get a sense of where you might have some slack in terms of not necessarily impacting your overall accuracy, even in the presence of mistakes. So going with that trial window example from the preceding point, you can see how short to make your trial windows in order to get as many trials as possible by keeping the trial window well above that minimum where people just start guessing, so that even though you know that they're making fast decisions that are pretty much faster than they would outside the lab, you at least know that within that range, you're still going to detect robust effects on their decision processes. Now finally, you can put together these prior points to provide a basis for detecting errors that, when put together, provide an arsenal for thoroughly evaluating a hypothesis. If you take all of these approaches, from before trial checks to simulating errors, understanding the effects of mistakes, amplifying errors, you can develop a system of a severe test of a hypothesis. And we're going to kind of focus in on this last point here, because what you're going to want to do is be able to create an experimental framework that is robust against sources of errors as possible, so that any true effects you see can be used in the evaluation of your primary hypothesis. This is what Deborah Mayo calls arguing from error. The argument from error relies on the idea of a severe error probe. After learning enough about certain types of mistakes, or errors as we've been talking, we may construct a testing procedure with an overwhelmingly good chance of revealing the presence of a specific error if it exists, but not otherwise. What this means is that if an effect is observed after all possible other sources of error have been accounted for or eliminated, then there is a very high probability that the true effect exists. If we can account for errors at the data model level and at the experimental level, then when we're evaluating our hypothesis at the primary level and we show evidence that allows for us to reject the alternative hypothesis that the effect isn't there or that our model is wrong, then we have allowed for our hypothesis to pass a severe test. It has very few other sources of error that could allow for us to accept an incorrect and null hypothesis. And this is the error statistics approach to inference. You essentially want to identify all potential other sources of error that could allow for you to falsely reject your null hypothesis, so that when you actually evaluate your null hypothesis and the evidence all says to reject it, you can feel comfortable in that rejection because you've eliminated all alternative sources of error. So now that we've gone over the error statistical approach, let's consider the differences between the inductive Bayesian approach and the deductive kind of frequentist approach that Mayo is proposing through a case example, and this is the example from the reading. So the example that was chosen in this debate between Mayo and another article in the same issue written by Hausen is the case of a breast cancer screening. The overall question is, given a test result or feedback, does a patient have breast cancer? So the scenario lays out like this. E is the evidence. In this case, it's an abnormal reading in the cancer screen. Now, the hypothesis that's being evaluated directly is the hypothesis that breast cancer is present. And in these sorts of tests, this is actually the null hypothesis. So you're trying to reject the probability that breast cancer is present given the evidence from a screening. The counter hypothesis is that the breast disease is absent. So you might get a likelihood of the result that you have given that H is true, or that breast cancer is present, be approximately equal to 1. You can further assume that if a person is not present with the disease, if the disease is not present, then she very rarely gets an abnormal reading, so that the probability of the evidence or the reading given that breast disease is absent is really low, 0.01. So in other words, if a person is disease-free, then the probability of an abnormal reading is very low. Now, in another article in this same series, Hausen provides a Bayesian criticism of the traditional inference approach towards evaluating the results of this cancer screening. So Hausen's argument is that the evidence is taken as failing to reject the null hypothesis that breast cancer is present, while also rejecting the hypothesis that the breast disease is absent, J. So in other words, an abnormal result is taken as failing to reject H, while rejecting J, that no breast disease exists. H, the hypothesis that the breast disease is true or present, passes a severe test, and thus H is indicated as having a high likelihood. However, and this is the important part, the base rate, i.e. the prior probability for breast cancer, is really low. The base frequency of this disease is low in the population. Thus, according to Bayes' rule, the posterior probability of H is also low. So that even though the evidence from the likelihood, given that H is true, is relatively high, the fact that the relative base rate is so low in the population, the posterior probability that you would get from an evidentiary approach is relatively low. And therefore, the conclusion is that H is not indicated, but J is from a Bayesian perspective. And therefore, the existential inference is unsound, because the existential inference would assume that this abnormal result is indicative of the presence of breast cancer. Now, Mayo's reply to this is that this is kind of a naive perspective on how to use statistical results, or the outcome of any test result, to evaluate a hypothesis. As she points out, there are systems of errors that could occur at multiple levels in the inquiry that could lead to an incorrect assessment of your hypothesis. So the error statistician perspective would say that E, the evidence, itself is not an indication on H directly, but depends on potential sources of error. Where could error have arisen so that you could look at this test result in the context in which the data was collected? So for example, E may be a poor indication of H, so the evidence from the test might be a poor indication of the presence of breast cancer if the probability of E is more extensive than the disease prevalence rate itself, D. In other words, if the false positive rate of the test is greater than the prevalence of the disease, you can't take that test result as being a good indication of the presence of breast cancer. In contrast, E would be a good indication of H. The test would be a good indication of breast cancer if the probability of E is more extensive than the disease prevalence rate itself. In other words, when the false positive rate of the test is much smaller than the disease prevalence itself. This latter part here would be a severe test scenario. So the point of this example is to show that the error statistician doesn't just look at the outcome of a single test result in order to make a decision about a hypothesis. You use this contextualization of sources of errors at multiple levels in the data analysis, data modeling, and hypothesis generation pipeline in order to come to a conclusion about the validity of H and whether or not you need to reject it. So, stepping back, what is the general take-home message from this lecture? Well, first, I think Deborah Mayo makes a very strong case that inferring the probability of a hypothesis requires a systematic awareness of the sources of errors at multiple levels of inquiry, from the data models level to the statistical or experimental model level, all the way up to the primary level of your theory and hypotheses themselves. Each one of those contains sources of errors that you have to account for in order to increase the rigidity or severity of the test of the hypothesis. And that evidentiary methods like the inductive Bayesian approach and existential methods like the deductive frequentist approach differ in their aims, with the latter being more directly accessible to evaluating sources of error. In other words, the error statistician approach allows for you to systematically characterize where errors may occur in order to make a guided inference as to whether or not to reject a given hypothesis.